Hi, I'm Rahul, and I'll be talking about how the minimum formula size problem is ETH-hard. So I'll begin with some background, and we'll start by defining the minimum circuit size problem, or MCSP, which is the minimum formula size problem's more famous cousin. So the minimum circuit size problem works as follows. So you get two inputs. The first input is the truth table T of a Boolean function f. So a Boolean function f is just some function that maps n bits to 1 bit, and its truth table is just the list of all the values the function takes on all of its inputs. And I want to stress that this truth table is a very long string, so if f takes n bits as input, then this truth table is going to be of length 2 to the n. And so our convention in this talk is going to be that we'll let capital N equal to 2 to the n be the length of this input, and that's going to be like the length of the input to MCSP. Meanwhile, little n will denote the size of the input to f. Okay, so the first input is the truth table of a Boolean function f. The second input is just some integer size threshold s. So just some size threshold that you get. And the output is going to be, does there exist a circuit with, say, at most s wires computing f? And to be really precise here, I have to define precisely what this notion of circuit is, and let me come back to that in a little bit. But hopefully the definition is clear. You basically get to describe a function using its truth table, and then ask whether or not there is a circuit of size at most s that computes that function. So what do we know about the complexity of MCSP? Well, it turns out it's not too hard to see that MCSP is an NP. If you want to witness a yes instance of MCSP, you can actually just hand over the circuit of size at most s that computes T. And the point is that because this truth table is so long, it's of length 2 to the n, you can actually go in and check whether or not that circuit computes the given function. And so with some work you can check that MCSP is indeed an NP. What is more difficult to see is that MCSP is probably not NP. It turns out that if one-way functions and all that great cryptographic stuff exists, then MCSP cannot be NP. And this is non-trivial to see, and I won't go into it so much, but what I would like to emphasize is that we have this problem MCSP, it is an NP, it's probably not NP. Probably the most natural question to ask is it NP complete? And that question is kind of the motivation for this talk and this work. And so finally I just want to end by saying, okay, I've defined the minimum circuit size problem, and for the next few slides I'll maybe talk about the minimum circuit size problem because it's maybe where the motivation for this work started, but you can probably guess what the minimum formula size problem is based on this definition. And so the minimum formula size problem, or MFSP, abbreviated, is this same problem. You get as input a truth table T of a Boolean function, a size threshold, but now you ask, is there a formula with at most s wires that computes the function f? Okay, great. So I've told you what the definition of MCSP is, and I've told you the definition of what the minimum formula size problem is, but I haven't told you why you might care about these things. And I don't have too much time, so I don't want to go into this too much, but let me briefly on one slide tell you why I think this problem is kind of interesting to study. Maybe the first reason to study it is that it seems like a natural problem. It's a very reasonable question to ask about circuits. If you're a circuit designer, or you want to understand how hard a certain function is, it's natural to study what its circuit complexity is. And so you might be interested in what the complexity of this problem is. What I think really draws me to this problem is the interesting connections it seems to have to other areas of computer science. So there are these really interesting connections between MCSP and the existence of one-way functions, and the ability to learn certain classes, and even to average case complexity, and worst case to average case reductions, and breakthroughs in circuit complexity. And it seems that by understanding MCSP and its degree of hardness, it could shed light on these things. In fact, its complexity is like really a mystery, as I've already mentioned. We don't know whether it's NP-complete, we don't know it's hard to approximate, we don't know any algorithm that's better than brute force, and it turns out that answers to these questions actually have important ramifications in these other areas. And so because of that, I think MCSP is an interesting thing to study, and it kind of motivates understanding it better. But I'll end it with that, and now return back to the main motivation for this work, which is MCSP NP-hard? And as I mentioned earlier, this is a long-standing open question. It goes all the way back to Levin, and in some sense even earlier than that. And you might ask, like, why? Like, we know lots of problems as NP-hard. Why does this particular problem seem to resist our ability to show that it's NP-hard? And the intuition I have, and I think many people have, is that if you look at the difficult no instances of MCSP, the ones you'd like to make use of in designing a reduction, those difficult no instances correspond to functions requiring large circuits. And the problem is, we don't have explicit functions requiring large circuits. This is like one of the long-standing goals in complexity theory, is to come up with explicit functions that require large circuits, and we don't know of any of them yet. So as you can imagine, that might make it difficult to design an NP hardness reduction, since we don't know any like non-trivial no instances of MCSP, at least explicitly. That makes it hard to design a reduction from SAT to MCSP. Indeed, there's a way to formalize this and say that like any deterministic polynomial time reduction from SAT to MCSP requires a breakthrough. And so what does this mean? Does this mean maybe we're not ready to answer this question of whether MCSP is NP-hard yet? Maybe we should come back to it when we have new techniques? I'm not so sure. In particular, something that I've been thinking about for a while now is what about sub-exponential time reductions? Maybe polynomial time reductions require some breakthrough, but if you only want to get a sub-exponential time reduction, is there anything really stopping you? In particular, if you like go in and look at this connection here, you might wonder, like, if I'm aiming for a sub-exponential time reduction, you could hope to get away with only using functions that require linear size circuits. And we know functions that require linear size circuits, so it's not clear whether this barrier applies to sub-exponential time reductions. Indeed, the motivating conjecture behind this work is that the exponential time hypothesis implies that MCSP is not NP. So under the exponential time hypothesis, that's what ETH is, it roughly says that SAT can't be solved in sub-exponential time. The conjecture is that shows that implies that MCSP is not NP. And I definitely think this conjecture is true. I mean, if one-way functions exist, this conjecture needs to be true. But what's actually more interesting about it is it seems like we should be able to prove it, and we should be able to prove it with the techniques that we have currently, maybe like a small step beyond that. Okay, so this conjecture is kind of the motivation for this work, as you can guess maybe by the title of this paper, which is that the minimum formula size problem is ETH hard. So let me tell you a little bit about the work that's come up to this conjecture so far, which is what we build on to show our main result. So, last year, we showed that ETH implies that partial MCSP is not NP. So the conjecture is that MCSP is not NP. What we're able to show is that the partial version is not NP. So what is the partial version? And this will be important for our result. So the partial version is MCSP for partial functions. In particular, the input is now the truth table of a partial function, and this is still a length 2 to the n string, except now the values in that string have 0, 1, and star in them. So now the function is allowed to evaluate to star. That basically means you don't care about that input, and some size threshold s. And then the output is, does a size s circuit compute that function when you ignore the star values? And so this partial version of MCSP, you can actually show it's not in P under ETH. And optimistically, one might hope that maybe we're just like one step away from the conjecture. In particular, there are reductions that are known from partial MCSP to MCSP in restricted cases, so for specific classes of circuits such as DNFs. This result here holds in the general case. It holds for the usual and or not fan-in 2 circuits. If one could give a reduction from partial MCSP to MCSP, then you could compose this ETH hardness result with that reduction, hopefully, and you could show that MCSP is not in P. So one might hope that if you can get a reduction from partial MCSP to MCSP, then you could resolve the conjecture. And indeed, kind of like our main technical result in this work is giving such a reduction for formulas instead of circuits. And so let me tell you about that. Our main result is as follows. The minimum formula size problem, or MFSP, is not in P under ETH. And so some things that I want to emphasize about this theorem. One, this is for the total function version of MFSP. Although the result does build on the result for the partial function version. Another thing is that the underlying notion of formulas here is the usual notion. They're De Morgan formulas and or not gates of fan-in 2. Another thing is, like, you might wonder how not in P is this under ETH, and it's just barely not in P. So the lower bound is about n to the log n. Here, recall that capital N is like the length of the truth table, and little n is the number of inputs to the function that's whose truth table is being given. And finally, I want to mention that this hardness result actually even holds when the size parameter s is kind of small. It's like polynomial in n. And if you look at this, this is like, these two lower bounds are not quite optimal. Like, this is the lower bound you'd expect if the size threshold, this is the lower bound you'd expect for the brute force algorithm, if the brute force algorithm is optimal. What if the size threshold is linear in n, but we're only able to give that lower bound when the size threshold is polynomial n. And I'll come back to that later when I talk about open questions. But in summary, we're able to show that this problem is not the minimum formula size problem, which seems, empirically really close to the minimum circuit size problem, is not in P under ETH. Okay, so that's our main theorem. So I'm going to talk a little bit about how it's proved in the technique section. But before I do that, I do want to mention one other thing. Oh, sorry. And the last thing I want to mention about this reduction is that, if you're interested, it's a deterministic sub-exponential time 2-query reduction. And the other thing that I want to mention is, building on the techniques used to prove ETH hardness, we also get something interesting in the search decision realm. In particular, it's been an open question for about 20 years now as to whether or not MCSP has a search decision reduction. And the interest in this is kind of motivated by NP completeness. Since SAT has a search decision reduction, that is, if you can solve the decision version of SAT, you can solve the search version of SAT, every NP complete problem also has to have a search decision reduction. So if MCSP is NP complete, it also needs to have a search decision reduction. Indeed, it's a necessary condition for NP completeness, and this was observed by Cabinets and Tsai, who in 2000 asked this question: does MCSP have a search decision reduction? And this has been open for a while. Kind of interestingly, building on the techniques we use to show ETH hardness, we can actually show that the minimum formula size problem does indeed have a polynomial time search decision reduction. And one thing that I want to emphasize here is that on the last slide we were talking about sub-exponential time hardness. Here we're actually talking about polynomial time search decision reductions. So that's interesting. And something that makes this result even more interesting is that this theorem, that it has a search decision reduction, actually does not relativize it. There's this result by Ren and Santhanam that shows that there are oracles relative to which MFSP doesn't have a polynomial time search decision reduction. So as a result, this theorem does not relativize. Okay, so I only have a few minutes left, so I am just very briefly go over some of the techniques we use in this paper. In particular, I want to just mention our approach for proving the MFSP hardness result, and it works by giving a fine-grained reduction from the partial function version to the total function version. So as I mentioned earlier, there was this prior work that showed under ETH that the partial function version of MCSP is not in P. It turns out if you look at it, that also works for the minimum formula size problem, and then crucially, it holds even when the size parameter S is very small. So under ETH, solving the partial function version of the minimum formula size problem is not in P even when the size threshold is equal to n. So even when the size threshold is very small. And what we do is we combine that hardness result for partial MFSP with a sort of fine-grained reduction from partial MFSP to MFSP. So in particular, we show that if you're given oracle access to MFSP, you can then solve the partial function version of MFSP in time 2 to the order s plus n, where s is the size parameter that you're trying to solve the problem on. So this running time here is like not ideal. I mean, it's exponential in s, but it actually is faster than the brute force algorithm. The brute force algorithm would take time like n to the s instead of 2 to the s. And in particular, if s is equal to little n, as is the case for this hardness result, then this reduction runs in polynomial time. So basically what we get is that we know that partial MFSP on this size parameter is not in P. We know that there's a polynomial time reduction from partial MFSP to MFSP in this size regime, and that gives us our main result, which is that MFSP is not in P under ETH. So let me describe this main lemma that we use to give the reduction, at least very informally. So the way that it works is we show that given any partial function f, you can construct related total functions g and h such that the formula complexity of f, that is the size of the smallest formula that computes f, is equal to the formula complexity of g minus the formula complexity of h. And the important part is that on the left-hand side we have the formula complexity of a partial function, and on the right-hand side we have the formula complexity of two total functions. And as a result, this gives you a way to connect partial MFSP to total function MFSP. I won't go into the details of how you construct these functions g and h because we don't have that much time, but I will say some notes about this lemma. There's a few things to note. Probably the most important thing to note is that there could be an exponential blowup in going from f to g and h. So g and h could require much more inputs than f, and this is kind of why the reduction we get is only this fine-grained 2 to the order s plus n reduction. Another thing is that we build off some prior work here, and in particular we use the leaf weighting technique of Buchführer and Ummans. And lastly, you can build on this lemma very carefully in order to get our search decision reduction. You need to be very careful because you really don't want to introduce an exponential blowup because the search decision reduction requires polynomial time, but you can indeed build on it to get the search decision reduction. Okay, so finally I'll end with some open questions. Kind of the most interesting question that I want to solve, the one that's been bugging me, is this main conjecture that we mentioned earlier. Does ETH imply that MCSP is not in P? But even coming back to MFSP, there are still some pretty interesting questions. For example, can you prove hardness of approximation for MFSP? The current result basically gives no hardness of approximation. You should be able to do better than that. Another thing is, can you get better hardness for MFSP? The current lower bound that we get is this n to the log n, which is barely super polynomial and is not even optimal for the regime of size parameters that we use. Can you get hardness there? So anyway, thanks for listening to my talk. If you have any questions, feel free to email me.